History has proven that those who dare to imagine the impossible are the ones who break all the human limitations. By breaking the limits of their imagination, they change the world.
From the vastness of space to the humble streets of India, there lies a story of ambition, perseverance, and triumph. This is the story of the Indian Space Research Organization. Founded in 1969, ISRO began as a modest dream, fueled by the vision of Dr. Vikram Sarabhai. His dream was simple, yet profound: to harness space technology for the nation's development and to explore the unknown. With limited resources but limitless determination, ISRO launched its first satellite, Aryabhatta, in 1975. From there, ISRO's journey has been nothing short of extraordinary. With each mission, they created new limits and further broke them.
One such significant mission was in the year 2008, named Chandrayaan I, India's first mission to the moon. This pioneering mission not only demonstrated India's capability in space exploration, but also made a significant scientific breakthrough by confirming the presence of water molecules on the lunar surface. A Chandrayaan I's success was a giant leap for India, marking its entry into the elite club of lunar explorers.
A decade later, in 2019, ISRO launched a follow-up mission, the Chandrayaan II, aiming to further unravel the mysteries of the moon's south pole. Though its lander Vikram experienced a hard landing, the orbiter continues to relay valuable data back to Earth, contributing to our understanding of the moon's composition.
And on this very day last year, on the 14th of July 2023, ISRO launched the LVM-3, aka GSLV Mark III, carrying the third follow-up mission in the series, namely Chandrayaan III,
which is yet another giant leap for India's space program. Chandrayaan III wasn't just about sightseeing on the moon, it was a scientific powerhouse. So what was its main goal? Its mission objective was to carefully land a lander and a rover near moon's south pole, a super icy, unexplored and mysterious region. But why particularly the south pole? Well, this region is thought to hold ancient water ice deposits, which could be key to understanding the moon's evolutionary history and maybe even finding signs of water. Chandrayaan III wasn't just about landing. This mission was packed with scientific equipments. The rover would be scooting around the lunar surface, analyzing the soil and rocks, while the lander will be studying the moon's environment from its prime location. The data collected by Chandrayaan III could tell us more about moon's formation, the possibility of water, and even pave the way for future lunar colonization. Join us as we embark on a spectacular journey into the Chandrayaan III mission.
Let's start our journey by taking a closer look at the various components of Chandrayaan III and delve into the details of this fascinating spacecraft. Chandrayaan III majorly consisted of three modules: the propulsion module, the lander module, and the rover. The propulsion module had the responsibility to carry the lander module from the launch vehicle injection orbit till the lander separation point. The lander module, named Vikram, was the actual component which touched down on the moon and helped create the historic moment for India. Safely tucked inside the lander was the rover named Pragyan. And upon the successful touchdown of Vikram, the rover was deployed onto the lunar surface. The rover and the lander stayed active on the moon for one lunar day, that is 14 Earth days, during which the rover covered about 100 meters. The rover had two scientific payloads to carry out experiments on the lunar surface. and upon the completion of the mission, the rover now stays there forever as India's lunar ambassador. These three main units collectively contained 7 scientific instruments, and let's cover each one in detail, starting with those housed within the rover.
Firstly, we have the APXS, short for the Alpha Particle X-ray Spectrometer. The APXS is a crucial tool in identifying the mineral composition of lunar soil in search of elements like sodium, magnesium, iron, potassium, silicon, and more. This would help scientists analyze the moon's major rock-forming elements, enhancing our understanding of its geological history. To understand how APXS functions, we need to understand the basics of spectroscopy. You might recall hearing about spectroscopy in school. If not, don't worry, we have got you covered. If we supply energy to molecules, causing them to exhibit various molecular vibrations such as symmetric stretching, asymmetric stretching, scissoring, and rocking. In case of spectroscopy, this energy is delivered in the form of light. And by varying the frequency of wavelength of the light beam, we can change the energy supplied to the molecules. Each element in the periodic table has a unique light spectrum defined by the light frequencies it can emit or absorb. Therefore, spectroscopy enables us to identify the elements present in compounds, as the diffracted ray matches specific electromagnetic spectra. Just like humans have unique fingerprints, each element interacts with light in a distinct way, absorbing certain wavelengths and allowing others to pass. This interaction creates a pattern of light and dark bands known as a spectrum. By examining which colors are absorbed or emitted, we can identify the substances present, similar to reading a barcode. In spectroscopy, light of different wavelengths is passed through compounds. Some wavelengths are absorbed by the compounds for the molecular vibrations mentioned earlier, while the remaining wavelengths pass through. These wavelengths are recorded for further analysis, and from that we can infer what the compounds were composed of. Now that we have gained a foothold of spectroscopy, let's get back to Chandrayaan III. The APXS used on Chandrayaan III utilizes this very concept and functions by irradiating the lunar samples with alpha particles and X-rays, and then analyzing the rays that pass through it to determine the elemental composition of the sample.
Now that we have learned about APXS, a very similar instrument on Chandrayaan III was LIBS, that is Laser Induced Breakdown Spectroscope, which uses a principle called Laser Induced Breakdown Spectroscopy to analyze the elemental composition of the lunar soil. It first vaporizes a small sample with a laser and examines the light emitted after passing through the vaporized form of the sample. And the best part, LIBS is a payload completely made in India, developed at the Laboratory for Electro-Optic Systems, Bengaluru.
Having explored the rover's intricate instruments, let's now shift our focus to the sole instrument of the propulsion module, the powerhouse that carried the hopes of an entire nation to the moon. It is called SHAPE, short for Spectropolarimetry of Habitable Planet Earth. But wait, why study Earth from the moon when we are trying to explore lunar mysteries? Well, SHAPE's purpose is actually to help us find habitable exoplanets. By observing Earth from lunar orbit, we can study the conditions necessary for a life-supporting planet from afar. Basically, SHAPE uses spectropolarimetry to measure both the spectrum and polarization of the reflected sunlight. This helps in understanding the composition and properties of Earth's atmospheric and surface conditions essential to sustain life. This data can be compared with observations of other planets and exoplanets, and thereby we can identify Earth-like characteristics in other celestial bodies, contributing to the search for habitable planets beyond our very own. The earlier concept of spectrometry is utilized here as well. By combining spectrometry and polarimetry, we lower the risk of false positives, thereby improving the efficiency of the results.
Finally, we will explore the 4 scientific instruments present on the lander. Firstly, the Laser Retroreflector Array, provided by NASA's Goddard Space Flight Center, is a device placed on the moon's surface. It reflects light sent from Earth back to Earth with minimum scattering. This prevents light from scattering in all directions, serving as a precise fiducial marker on the moon. In case you don't know what a fiducial marker is, fiducial marker refers to an object in an image which can be used as a point of reference or measurement.
Before getting into the next instrument, here is an interesting fact about the moon. Did you know the moon has its own plasma environment? But first, what exactly is a plasma? We know that if we heat a solid, it becomes a liquid, and we heat that again, it becomes a gas. But what if we further heat the gas? Well, the atoms present in the gas lose some of their electrons. It creates a stream of free electrons which aren't bound to the nucleus. This state is called a plasma, and this would be electrically conductive and able to respond to magnetic fields. Examples include the sun, lightning, and auroras. The moon too has its own plasma environment, and to study some of its characteristics such as electron temperature, density, and electric potential, Chandrayaan III carried a device called the Lunar probe.
The third instrument on the lander is called CHASTE, short for Chandra's Surface Thermophysical Experiment, which measures lunar surface temperature and heat flow and checks temperature changes up to few centimeters below the surface. And the last instrument in the lander is the Instrument for Lunar Seismic Activity, ILSA, to understand the seismic activity of the moon and to map out its crust and mantle.
With the help of all these instruments, we have glimpsed the moon's hidden depths and have made strides in lunar exploration. The Vikram lander studied the moon's ionosphere, successfully measuring its electron densities. Additionally, the Vikram lander's seismograph managed to record a short but significant seismic event lasting 4 seconds. The Pragyan rover found the presence of sulfur on the lunar south pole. The lander had also conducted the first ever measurements of the near-surface lunar plasma environment of the South Polar region. Saving the best for the last, the Vikram lander also conducted a HOP experiment which gave scientists a hope that it might be useful to bring back lunar samples to Earth someday in the future.
All these experiments and results will help shape the future of Indian space research in the fields of developing communication technology for the moon, while giving us insights about lunar geological activity and geochemistry of the lunar surface. The Chandrayaan program, conceived as a modest idea in 1999, has blossomed into an incredible journey for India. Chandrayaan III's historic soft landing on the moon's south pole marked India as the fourth nation to achieve this feat and the first to do so in this challenging region. This mission's groundbreaking discoveries, from detecting sulfur on the lunar surface to measuring the moon's sparse plasma environment, have not only expanded our understanding of Earth's celestial neighbor, but also paved the way for future lunar exploration and potential resource utilization. These achievements underscore India's growing prowess in space technology and its significant contributions to global lunar research.